Hello, this is Mr. Gilmore with the 12.1 surface area of simple solids. We are going to be moving into three-dimensional figures here in chapter 12. We're going to first begin by looking at what surface area is of three-dimensional solids. We'll define a few terms and then jump into actually finding the surface area of some simple solids. In our next lesson in 12.2, we will be finishing the chapter by looking at the volumes of those simple solids. So let's begin today's lesson. So, what is a solid? A solid is a closed three-dimensional figure. So think about any sort of three-dimensional object, such as a ball or of a cone. We could also think about as some sort of box. We can fill that space that's been filled, and when we fill that space, we measure that. And we measure that in terms of what we call volume. Now, we won't be investigating what volume is today. We're looking at what's called surface area. So before we get into finding some of the surface area of these solids, we actually have a specific name for solids that are composed of only polygons. They're called polyhedron, or for the plural, it's polyhedra. And then when we look at a polyhedron, because all of the faces are these simple polygons that we worked with, we're going to look at each of the parts and give them some jargon. So we first, by looking at each of the flat planes that are the surfaces that make up the solid, we're going to call those faces. Where those faces intersect, we're going to say that they intersect along what's called edges. And then where those edges actually intersect, we're going to call them vertices. So I've got a diagram of this. Let's take a look at what that looks like. So here's a cube or some sort of rectangular prism, and each of the faces we see. So yes, you want to look at it from a perspective of a three-dimensional figure. We see the face is the actual plane. Where those planes intersect, we call those the edges, and then where the edges intersect, we call that the vertex. Now, in a prism is a special type of polyhedron. We are going to use those same that same jargon of faces and edges and of the vertices, but we have some specific names we want to give to the faces of a prism. So a prism is a polyhedron with a pair of congruent parallel bases. So in our diagram below, we actually see that the bases here are actually hexagons, and those hexagons are parallel to each other, so those planes will never intersect, and they're congruent. So they are the same size, same shape, which means they will have the same area as well. And then when we join those hexagons together, connecting them with these other planes, those are what we call the lateral faces. And so when we find the area of a prism or really of any solid, what we're doing is we're figuring out what is the area of each of those polygons that make up its surface. Thus, we call it the surface area. Now, there are some differences. We have what are called right prisms and we have what are called oblique prisms. So a right prism is where we find a prism to be directly over top of the base directly over top of the other, forming a perpendicular, which means the lateral faces are all rectangles. Whereas an oblique prism is where the bases are kind of shifted over. They're not quite directly above and below each other, which means that the lateral faces change. They're no longer rectangles. They don't form these right angles. They are actually parallelograms. And we'll be seeing that we're going to be sticking with the right right prisms in this lesson. We will take a look at some oblique in the volume, but with surface area, it's nice to know that our lateral faces are rectangles, and so we'll stick with that. Now, how we give prism names is based on their bases. So the very first adjective you want to apply to a prism is either the adjective of right or the adjective of oblique. So down below, the first prism we see is the adjective of a right prism. The second one is of an oblique prism, but we also insert a second adjective, and it's the adjective that we use to describe what the shape of the base is. So for example, the base in the first is a hexagon. So to name that one, we would say that's a right hexagonal prism. Hexagonal is that another adjective we use for that prism. In the second diagram, though, we have a pentagon as the base. So that's called an oblique pentagonal prism. Now, we're only going to be working again today with right prisms, but you'll see that we'll be investigating different types of right prisms, such as a right hexagonal prism or a right rectangular prism, things of that nature. So yeah, we will stay away from the oblique today. Let's take a look at the right prism surface area theorem. We can actually prove this formula below, and we're going to forego that proof and just jump right into what is this proof saying. This proof is actually boiling down the ability for us to find the surface area of any given right prism. And the way it boils down to is this very simple formula at the very bottom. Let me break down each one of these variables for us. So SA just simply stands for surface area. We know that. This capital B here, that is actually going to be known to us as what we call the base. Okay, it's going to be called the base. So we're going to call this guy, this is the area of the base. P, we've seen this capital P before as well. Capital P is going to be known to us as the perimeter of the base. And then H is actually what we call the height of our prism. Now, the height of our prism will be that measurable distance along the lateral face, or essentially the height is going to be this distance between the two bases. So we're going to take the area of the base, we're going to take the perimeter around our prism, and we plug these into our formula. 2 times the base plus the perimeter of the base times the height, and that's going to actually result in the total surface area of the entire prism. So let's actually take a look at an example of using this. So below we have a right hexagonal prism, and what we're going to do is we're going to find the total surface area of this. And the way we do it is by actually breaking it up into finding the area of the base, the area of the lateral surfaces, and we add them together to get the total surface area. And so that's where our area formula comes into. So the surface area formula, again, for any right prism is 2 times the area of the base. That's going to give us the base surface area plus the perimeter times the height. That's going to give us the lateral surface area. And then when we add them together, it's going to give us the total surface area of our prism. That's what we're looking for, this total surface area. So what we need to do is figure out the area of the base, the perimeter of the base, and the height of our prism. Well, the height of the prism is where I like to start. That's usually the easy one that's given to us. It's a height of 18. Now, the perimeter of the base is another easy one to find. We're given the side length of this hexagon. One thing to safely assume about these bases is that if it appears regular, it is regular, which means all 6 sides here are going to also measure 6. So we can find the perimeter of our base is 36, 6 times 6. Now, we also need to find the area of our base, which means we have to find the area of a regular hexagon. We did this in chapter 11. For time's sake, I'm going to go ahead and save us some time and go ahead and copy down the area of this. This is the area of the base is 54 root 3. So now we have all 3 variables we need. We have the base, we have the perimeter, we have the height. Check, check, check. Let's plug in our information. So our surface area is 2 times the area of the base plus the perimeter times the height. And we just simplify this. So 2 times 54 is 108 root 3. And then 36 times 18 is 648. And there we have it. That is the total surface area. Now, I can't add those terms together. They're not like terms because of that radical 3. But there we have it, an example of finding the surface area of a right prism. Let's take a look at what a pyramid is. So a pyramid is another type of polyhedron. Now, in this case, a pyramid only has one base, and its lateral faces this time are not rectangles, but they are triangles. A few of the jargon that we're going to be using is where these triangular faces intersect. They all have a common vertex right here at the very tip top of our pyramid. We're going to give that a name. We call that the apex of our pyramid. One thing that we'll assume about the apex is that it is directly above the very center of our base. So there's this altitude we'll talk about here in a moment. It's directly above the center of our base because we could have right pyramids and also oblique pyramids, but we're going to stay away from oblique pyramids and just focus on the right pyramids when we find surface area. So as we dissect the pyramid, there's actually a couple other jargon words we're going to be using. There's the lateral faces. Again, so we use that word lateral, but it's in reference to the triangles and not the bases. So I know this line looks like it's pointing to the base, but it's actually pointing to this front triangle. So those are the lateral faces. Now, there is another type of height that comes along with pyramids. There is a what we call a slant height. Okay. Now there is also this altitude that drops in there. We'll take a look at that in a little bit. So the slant height is as if you were to grab a sled and stand at the very tip top of our apex and slide down the side of our pyramid at a right angle to the base. Bam. when we hit that right angle there, that's what we've just traveled along the slant height. So it's not actually the actual height of our pyramid, but it is a slant height. We're going to look at there's a relationship between the slant height and the height here in just a second. So the last thing to consider is what is the height of the pyramid? Again, this is if we were actually to get on the tip top of our pyramid here at the apex, and we were to drill a hole straight down all the way to the very bottom of our pyramid. The distance we just drilled was known as the altitude. Now, the altitude has a length to it, which is then going to be known as the height of the pyramid. So notice it's not the slant height; it's actually the height of the pyramid. It's this perpendicular distance to the base, not as if we slid down the side, but actually drilled right through the middle of it. Okay. Now, slant height and height are not the same. Take a look at this diagram here. So you see there's a difference, right? Height is this straight drill down to the base at a right angle, but the slant height is actually sliding down the face or the lateral face of our pyramid, still at a right angle to the edge of our base. But there is a relationship, there's this connection we're going to talk about here between the slant height and the height of a regular pyramid. So here's what that connection is, that when you actually drop in the height and you drop in the slant height and you connect the two with the segment at the base, it turns out that that segment that connects them is the apothem. Yes, it's the apothem of the regular polygon. And because we're dealing with just regular polygons, we know that apothem length will all be the same. But what happens is because the height is perpendicular, we actually form a right triangle, which means the connection between these three is the Pythagorean theorem, which we're going to actually have to use here in an example coming up. We're actually going to use this connection to help find the surface area of our pyramid. If we're not given we're actually going to need the lateral height. So we're going to need the lateral height, or sorry, the slant height of. This is what we need. So if we don't have that, we got to figure out what that is, and I'm going to show you how to do that in our next example. But before we get to that example, I've got to give you the formula to find the surface area of a pyramid. So here's what the pyramid surface area theorem states. Again, we're looking for total surface area. To find total surface area, we add the area of the base, which is B again, right? There's the area of the base. And we add that to 1/2 the perimeter of the base times the slant height. That's where we get this 1/2 PL. So P represents the perimeter of the base and L represents the slant height. And with all three of those pieces of information, we can actually find then the total surface area of a pyramid. Let's take a look at an example of using this surface area formula to find the surface area of a pyramid. All right. Now, again, one assumption you can make about the bases of all the pyramids we'll be investigating is that the bases are all regular, meaning all sides are equal, all angles are equal. So this is actually a square pyramid. The square base means if I give you one side, you know all the sides. And in order to find the surface area, again, let's break down what that surface area formula is one more time. It's the surface area is the area of that base plus, okay, plus 1/2 the perimeter of the base times the slant height. Now, we can find the base and the perimeter of the base fairly quickly. Let's find the area of the base first. So the area of the base, remember, is a square. So it's just simply I take 18 and I square it. So the area of the base is 324. Not that bad to figure out. The perimeter of the base, also easy to calculate. It's 18 times 4, right? Because we want to know the distance around the square, and that would be 72. But here's the tricky part. We got to figure out what that slant height is. Notice that they don't give us the slant height. They give us the height. It's the altitude of the pyramid, which is 24. We got to figure out then what the slant height is. Remember, there's a relationship. It's the height squared plus the apothem squared is equal to the slant height squared. Well, we have the height. It's 24. The apothem is actually really easy to find out with a square. The apothem, remember, is this distance that is from the center of our polygon perpendicular to the edge. Well, as it turns out, in a square, it's half the length of the side, which means the apothem length is going to be 9. So we plug that in. 9 squared is equal to L squared. Now, to save on some time, I'm going to go ahead and solve for L for us. And when we do that, we get a simplified answer of 3 times the square root of 73. So there now is, check, Okay, we don't know what it, or we didn't know what it is, but now check, we know what the slant height is. We have all three variables we need. So now let's plug those into our formula. So it's the area of the base plus 1/2 the perimeter of our base times the slant height of our pyramid. And when we simplify that, well, it turns out that 324 actually can't be added to this next term because of that root 73, but we end up with 108 root 73, and there is the surface area of our pyramid. There it is, using our surface area formula for a pyramid. So make sure you have that written down. Okay, let's move on. Let's talk about a cylinder. So a cylinder has two bases, very much like a prism, but those two bases are going to be disks, or essentially they're going to find the area of circles. So in a cylinder, the bases are always the same. They're always these disks or these circles. The lateral face is actually kind of interesting. If you were to actually cut this open and lay out these pieces flat, the lateral face is actually a rectangle. But there is a formula to find the surface area of a cylinder, and a lot of you guys may know this. So let's actually take a look at the surface area formula of a cylinder. So the cylinder has two parts because it's the part for the two bases, that's part one, and then the part for the lateral faces. But when you find the area of the two bases, the area of a circle is always pi r squared, you double it. That's the first part. The second part is find this area of this lateral face, which actually, when you unroll it, turns out to be a rectangle. The area of that would be the surface area of that rectangle is then 2 pi r h. And so this is our cylinder surface area for any given cylinder, 2 pi r squared plus 2 pi r h, and we can find its total surface area. So all we really need to be given is the radius and the height, and we can find out its area, surface area. Let's do an example. So we're given this cylinder with a diameter of 12. And again, I'm not concerned with units. You shouldn't be concerned with units either. So I'm just going to drop units off. So diameter is 12, which means I know the radius is 6. The height, right, is the distance between the two bases, which in this case is 10. That's all we need is the radius and the height. So now we can use our surface area formula. Surface area is 2 pi r squared plus 2 pi r times h, and we just plug in what we get. The radius is 6. The the height is 10, and we simplify this. All right, so what we have 2 pi 6 squared. When we simplify that, we get 72 pi. And over here, when we multiply that out, we get 120 pi. Notice I'm leaving pi in my answer. And actually, what's interesting is these are like terms. 72 pi plus 120 pi, we can add those together, and we get a total of 192 pi. And there is our total surface area for a cylinder. All right, let's move on. Let's take a look at a cone. So a cone is very much related to like a pyramid where it only has one base, but the base is not, again, a polygon, it's a circle. So the base is actually this disk again, and we're going to find the area of that disk. Now, the lateral face is kind of a complicated figure. If we were to actually cut this into the two-dimensional planes and lay them flat, the lateral face of a cone actually kind of looks like Pac-Man. If I were to draw the flat part, it kind of looks like this. So it's kind of, you have to figure out how do you find the area then of something like that, and that's where we're going to look at a formula. There is a proof behind it, but we're just going to forego the proof and jump right into the formula. And so, very much like a pyramid, we have the lateral faces, we have the base, and we have that apex, which is that common point where our lateral face comes to a point at the very top. Okay, let's take a look at a couple other relationships with the cone. Like the pyramid, it also has a slant height. So the slant height, again, is if I were to sit at the very tip top of this cone and slide down the side of the cone, wee towards the bottom, I actually follow along the slant height. If you notice, the slant height is different than the actual height of the cone. Okay, so the slant height and the height are different again, but there is a relationship. It's a similar connection. So the slant height and the height, again, if we were to connect them with a segment, they form a right triangle. That segment that connects them is the radius. So our connection changes a little bit, where it's the height squared plus the radius squared equals the slant height squared. So it's not the apothem anymore, but we see that there's actually a relationship between the apothem and the radius of a circle. And so this is the new connection you'll be seeing, and you'll have to use that on some of the problems to, if you're, because you're going to actually need the slant height again. This is what you're going to need. which means if I give you the height, you got to turn it into the slant height. So that's the one you're going to need. So let's take a look at an example. Oh, sorry, let's look at the formula and then let's look at the example. So the formula is also, again, two parts. It's the part for the base, which is a disk. So it's just pi r squared, the area of the circle. And then for that unique lateral face, which looks kind of like a Pac-Man, this is what it boils down to. It actually turns into pi RL, which again, R is the radius, but L is the slant height. And so we're going to use this formula to actually to figure out the surface area of a cone in our next slide here. So here's an example. Here's a cone. From the diagram, again, I'm going to forego the units, but from the diagram, I can find that the radius of our circle is 5, and 14 does represent the slant height, so I know that L is 14. Now all I need to do is plug this into my surface area formula. So the surface area is pi r squared, that's the area of my base, plus pi RL, that's the area of the slant, or the area of that curved lateral part of our cone. So let's go ahead and plug in what we have here. It's pi times 5 squared plus pi times 5 times 14. If we simplify each of those parts, 5 squared is 25. Over here, we end up with 70 pi. Again, I'm leaving pi in my answer. And you see, oh, look, those are like terms. 25 pi plus 70 pi, it turns into 95 pi. And there we have it, the total surface area of our cone. So on the worksheet, you also see some examples of finding the lateral area, or sorry, the surface area of a cone. Now, for our very last piece of today's information, we're going to look at another roundy kind of thing. We're going to look at the sphere. So, a sphere is a set of points in space equidistant from a given point. So, we have kind of an example of a sphere given to us in the diagram. Remember, it's as if we took a circle's definition and we said, remember, a circle is a given set of points in a given plane, right? A given distance from a point. Well, if we remove the plane part from the definition, then it turns that circle into a sphere. If we just said, hey, a sphere is a set of points that are a given distance away from a given point, then bam, we've got ourselves a sphere. Now, spheres do have surface area formulas to them. They're actually kind of a neat proof behind it. We're going to forego that proof again and just jump right into the surface area of a sphere. Here's the surface area formula for a sphere. It is simply 4 pi r squared. Now, I don't have an example in the next slide, but the example would be pretty simple to use. If I were to give you the radius, let's say is 4, then all you got to do is plug that in. So then the surface area of our sphere would be 4 times pi times 4 squared, and we simplify that, that would end up being 64 pi is the surface area of that sphere. So it's very simple. Just find the radius of the sphere, find the radius of the sphere, plug it into a formula, simplify it, leave pi in your answer, and bam, you've got the surface area of a sphere. But there's also one last three-dimensional solid we can look at, and that is a hemisphere. So a hemisphere is a capped half sphere. So imagine taking a sphere, chopping it in half, but then there's kind of this open part of the sphere. So we got to cap it. So we put this circle or this disc on that capped part so that we can finish off and complete the fully closed solid. So that means there is this curved area, right? This curved area that goes around the sphere, or the hemisphere. There's also this flat area here that we're going to add to our surface area formula. So the very last formula we're looking at today is the hemisphere surface area formula, and here is the hemisphere for surface area formula. Now you're thinking, hey, wasn't the sphere surface area formula 4 pi r squared? Why is it not just half of that, 2 pi r squared? Well, remember, the half of that is this curved part. Okay, half of that is the curved part of our sphere, but we capped it, which means we added this flat part to the bottom, and that is a circle, which means it's another pi r squared. So we take the 2 pi r squared here, and we add it to the pi r squared on the bottom, and that's where we get 3 pi r squared. And again, I don't have an example for this one, but I can do a really quick example. Let's say the radius of our sphere is 7. So let's plug that in and find the surface area of our hemisphere. So the surface area is 3 times pi times 7 squared. 7 squared is 49. 49 times 3 is 147, and we get 147 pi is our surface area. Okay, so just an easy example of using the surface area formula of a hemisphere. Well, that concludes our surface area formula lesson. I apologize, it was a lot longer than I anticipated it to be, but this does cut our time down significantly shorter to just 2 lessons. So be working on the 12.1 worksheet on finding the surface area of our three-dimensional solids that we've covered today. And with that, be good and do good.